If your RAG keeps citing old documents, here is a simple chunk ID and upsert pattern that keeps the index consistent. Many systems end up answering with stale facts because their vector store still contains outdated chunks. By the end of this video, you will understand a stable chunk ID pattern and an idempotent upsert flow that prevents redundant writes and makes deletes safe. No advanced math, just consistent identifiers and simple hashes. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Updates and deletes in a vector index solve a very practical problem. You want a retrieval-augmented system that reflects edits and removals in your source content right away. Success means searches return current text and never point to deleted paragraphs. This pattern scales from a single document to thousands of documents, and it cuts down on wasted writes and surprise answers. At a high level, the idea is simple. Split a document into small chunks. Give each chunk a stable ID based on the document name and chunk position. Store a content hash with each record, so you only write when the text actually changes. When you need to remove a document, delete all keys that share its prefix. This keeps references stable for downstream systems while allowing content to change. We will build a tiny mock index for one document called doc.a. Show idempotent upserts. Run a toy similarity query. Update a chunk and requery, and finally purge stale chunks. That way, you see both the write and delete paths before you adopt the pattern in your project. This snippet initializes a mock vector index with stable chunk IDs and hashes. We create a store dictionary to represent the index and define doc.a as two small chunks. The item's comprehension builds records keyed by stable IDs derived from the document name and chunk index. Each record stores a content hash, computed with hashlib MD5, alongside the raw text. We then update the store with these items to simulate the first index build. The printed count confirms that the initial chunks are present and ready for later updates or deletes. Now we will show how to make upserts idempotent to avoid unnecessary writes. This snippet performs an idempotent upsert to avoid redundant writes. The variable changes counts how many records are written. For each chunk T, we build a stable key K and compute its current hash, H. If the key is missing or the stored hash differs, we update the store and increment changes. Otherwise, we do nothing. This mirrors a production upsert that skips identical payloads to save latency and cost. The printed value shows that reapplying the same content produces no writes, signaling a clean, idempotent path. Next, we will run a minimal relevance ranking so you can see how pieces are retrieved. This snippet ranks chunks using a tiny keyword count embedding and dot similarity. The list keys defines lightweight features, and M converts text into a small vector by counting those keywords. The function sim computes a dot product to score a candidate against the query vector Q. We then select best with max over the store, using the score as the key. Increasing the number of keywords can improve recall, but adds a small CPU cost per query. The printed ID reveals which chunk currently ranks highest for the query. Now we will edit one chunk, upsert the change, and check that retrieval follows the new text. This snippet updates a chunk via content hash and requeries to validate changes. We modify the second chunk text in doc.a and compute its new hash H. Using the stable key K, we conditionally upsert only if the hash differs, ensuring idempotent updates. A new query vector emphasizes the usage keyword, and we rank again with the same scoring routine. The stable ID remains the anchor while content evolves, which keeps downstream references predictable. The printed ID shows the updated chunk is now the most relevant for the adjusted query. Next, we will remove all chunks that belong to a document prefix to model a purge. This snippet deletes stale chunks by prefix, modeling a doc-level purge. We collect all keys that belong to the document prefix and iterate over a snapshot of keys to safely mutate the store. Each deletion removes outdated vectors, preventing the RAG system from answering with obsolete content. In a real sync, you would derive the expected ID set for the doc and delete whatever is not present after upserts. The printed count confirms how many chunk records were removed, proving the delete path works. To map this toy flow to a real system, treat the store dictionary as your vector database entries. The stable ID becomes the unique key you store alongside the vector and metadata. The same hash trick works whether you store full text, embeddings, or both. In production, compute hashes at ingest, batch upserts, and run deletes using the prefix or a membership list derived from the latest source snapshot. Recap: what it is, when to use it, and one caveat. It is a stable chunk ID plus hash-based upsert pattern that makes updates and deletes deterministic. Use it when documents change frequently or when you need reproducible references for downstream systems. One caveat: if your chunking strategy changes, you must plan how IDs map across schemes, or you will orphan old vectors. Next step: increase the number of keywords used to build the tiny embedding, or swap to a proper embedding model so you can measure recall and query latency under a larger corpus. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.